Hey YouTube, this is Mike, also known as the Wizard of Odds, and the goal of this video will be to show you how to program the casino game of blackjack in C++. You may have seen my other videos where I analyze blackjack in Excel. However, those use an infinite deck assumption, and in this video we are going to assume 6 decks of cards. Other rules that we will assume are the European no peeking at the whole card rule. We will assume the dealer stands on a soft 17, no doubling after a split. The player may split only once, and nothing unusual like drawing 2 split aces. So you can see that right now all our program does is say hello world. In fact, let's run it. And there you can see hello world, and we're going to go all the way from this single command all the way up to hopefully analyzing the whole game of blackjack. So let's see how it goes. Next, let's get our hands dirty, and we will do that by starting at the end with the dealer's hand. And what we want to know is the probability of the dealer getting a total of anywhere from 17 to 21, busting, or getting a blackjack. However, first let's introduce an array called deck, and that will have the number of cards left of any given rank left in the shoe. And as I believe I said earlier, let's say that this is a 6-deck shoe. So let's make a global variable called numDeck equal to 6 to represent 6 decks of cards. And now let's initialize this deck array. So let's let elements 1 to 9 represent the number of aces to 9s left in the deck, which is going to be 4 times the number of decks. Element number 10 is going to be the number of 10-point cards left in the deck, which will be 16 times the number of decks. And element number 0 will be the total number of cards left in the deck. So next, let's create a function to analyze the dealer hand. And let's call it just dealer. And this is going to be a recursive function. In other words, it's going to keep calling itself until it reaches a total of at least 17. And we're going to pass to this function some information that we'll need to know, like the total. And I'm going to call the total that gets passed to the dealer function the old total, and we will adjust that as the dealer hits, or should I say takes more cards. We need to know if the dealer has at least 1 ace for purposes of soft totals. And we need to know the number of cards, because it's a special case if the dealer has 2 cards with 1 10 and 1 ace, in which case he has a blackjack, which beats any other hand. And we need to keep track of the probability of any given state. We'll do that with a floating point variable. We need to know the deck composition at any given state. And our goal will be to populate an array that I'll call dealer probabilities, or dealer prob, for the probability of any given dealer outcome. And before I forget, let's define what those dealer probability values can be. So element number 0 in the array will be for a total of 17, 1 will be for an 18, 2 for a 19, 3 for a 20, 4 for a 21, 5 for a blackjack, and 6 for busting. So let's think of something arbitrary to pass to the dealer array. How about we'll start with a 5. which has 0 aces, 1 card so far. We'll pass to it 1.0 for the probability of, to represent this is the starting probability 1, and we will keep multiplying by 1 by probabilities of getting any given card as we go. The deck array and the dealer probability array, which we did not declare yet. So let's do that. So the first thing we'll do in the dealer probability is initialize that dealer probability array if we just called the function with just 1 card. So if there's just 1 card, then we're going to initialize that array. Then we're going to cycle through from 1 to 10 the possible ranks that the dealer could get as his next card. So let's call that next card just next card. And that can be anywhere from an ace to a 10. So the first thing we'll do is we're going to multiply the probability of the state we're in by the probability of getting any given card. And that's going to be the number of cards left in the shoe of whatever rank the next card is divided by the total number of cards left in the shoe. Then let's decrement by 1 the count of the number of cards of the next rank, as well as decrement the total number of cards left in the shoe by 1. So we just gave the dealer another card. So let's create another variable called new total, as well as new ace, to represent the adjusted number of points in the dealer's hand and the adjusted number of aces. So the new total is going to be equal to the old total plus the next card. And the new number of aces is going to be the old number of aces plus, if next card is equal to 1, we're going to add 1 to the number of aces. Otherwise, we will add 0. So first, let's consider the special case where the dealer has a blackjack. What are the conditions that must be met for the dealer to have a blackjack? Well, he should, in the real game, have 2 cards. But the dealer array initially is going to get past 1 card, and then we give him another card in this loop here. But the value for the variable cards will still be 1 at this point. And the new total will be 11, because the dealer will have a 10 and a 1, and the number of aces will be 1. That will, if all those are true, then the dealer has a blackjack. And if he does, then we're going to increment element number 5 of our dealer probability array by the probability of the state we're in. And that probability being the probability of a dealer getting a blackjack. In that order. Could either be ace 10 or 10 ace. Otherwise, another special case is the dealer busting. So if the new total is greater than 21, we're going to increment element number 6 of our dealer probability array by the probability. Otherwise, if the new total is greater or equal to 17, then we're going to stop drawing cards and increment the dealer probability array according to whatever the new total is. And we can get to the right element in the array by subtracting 17 from the new total. Now, what about if the dealer has a soft 17 or more? We can check for that if the new total is greater or equal to 7 and the new total is less than or equal to 11 and the number of aces is greater than 0. So that will mean that the total number of points is in the range of 7 to 11 with at least one ace. With the ace, we can kick in another 10 points to the total to get into that sweet 17 to 21 range. And here we're going to subtract just 7 from the new total to get to the right element in the dealer probability array. The alternative to all these possibilities is that the dealer has 16 or less points, in which case the dealer needs to take another card. And we're going to represent doing that by calling the dealer function itself. And we're going to pass to it what is now our new total, the new number of aces, the new number of cards, which is going to be the old number of cards plus 1, the probability, the deck array, and the dealer probability array. And after all that, we're going to clean up after ourselves by putting back into the total number of cards 1 when we are done examining the last card dealt, and 1 for whatever that rank was that was just dealt at this level in the dealer probability recursive array. And finally, again, in the interest of cleaning up after ourselves, we're going to divide by the probability of getting the last card to get to the state, to get to the probability state that we were in before that last card was dealt. So let's go back up here. So here's where we called the function, passing it to it just a 5. And let's show what comes out of the dealer probability array once we go to it. So let's show the probability for the 7 possible values of the dealer probability array if it gets past a 5. And we don't need the hello world anymore. And I forgot, as I often do, to declare this function. So let's compile this. It compiled, and let's run it. So here we go. This is telling us that if the dealer starts with an up card of a 5, he has about a 12.2% chance of getting a 17, 12.2 of getting an 18, 11.8 of getting a 19, 11.3 of getting a 20, 10.8 of getting a 21, 0 of getting a blackjack, and 41.6 of busting. And these numbers look reasonable to me. So let's see what happens if we pass to the dealer function any given up card. Let's switch to C out. So here we're going to pass to it instead of 5 an I. And for the number of aces, we're going to pass to it a 1 if I equals 1, otherwise a 0. So let's compile this and run it. But before I can run it, I made a commonly made mistake of having a nested loop with the same variable name. So let's add a J here for this loop right here within the I loop. I did find one minor mistake. So you recall here that I was cycling through the various 10 dealer up cards, and I forgot to take them out of the deck as I went. So let's correct for that. So here we are taking away 1 from the number of whatever the rank is and the total number of cards. And let's add them back in here after we're done passing to the dealer function. So let's compile that and run it. And here we get our corrected results. And these look not just in the right ballpark, but exactly right to me. So I will see you in the part 2 of this series when we get to the player hand. Next, let's write a function that calculates the expected value if the player stands. Let's call it player stand. And we need to pass to it the player's number of points, whether or not the player has an ace, or in this case the number of aces, the number of cards, which is important for testing for a blackjack, and the deck composition. So let's declare some variables. Let's call EV stand, the expected value of standing. And here is our probability for the dealer array. So first let's test for a player blackjack. So if the player has 11 points, remember aces count as 1 unless otherwise stated. And the player has an ace. And the number of cards is 2. Then we have a blackjack. And if the up card is greater than 1 and less than 10, then we have a winning player blackjack. In which case we can just return 1.5 and be done with it. Doesn't matter what the dealer has. Otherwise, the dealer does have a possible blackjack because he has an ace or a 10 up. So we're going to need to call that dealer probability, our dealer function. And remember, we pass to that the up card, whether or not the dealer has an ace. So at this point he only has one card, and if that card is a 1, then he has one ace, otherwise 0. Whoop, this should be a colon, not a comma. Next, we pass to it, let me remind myself, the number of cards, which is 1, 1.0 for the initial probability, the deck array, and the dealer probability array. And I forgot to declare deck as an array, and before I forget, let's make a global variable for the up card. So after we come back from the dealer function, we're going to have those dealer probabilities, and we're going to, the player is going to win 1.5 if the dealer has a 17, 18, 19, 20, 21, or busts. So those are going to be elements number 1, 2, 3, 0, 1, 2, 3, 4, and 6 in the dealer probability array, skipping over 5 for a dealer blackjack, which is a push. Otherwise, what if the player has over 21 points? Then the player busted, and we can just return a -1. And I forgot my semicolon here. Otherwise, we have a player hand of 21 or less points. So first let's adjust it if it's a soft hand. So if the player has 11 or less points and 1 or more aces, then we have a soft hand, in which case we can add 10 points to the total. Then we're ready to call the dealer function. Then we can start out the expected value of standing as the probability of the dealer busting. Then we can subtract from it the probability of a dealer blackjack. Otherwise, let's cycle through the values of a dealer 17 to 21. So if the player total is greater than I plus 17, then the player beat that total, in which case we can add to the expected value of standing the element in the dealer probability array for that value. Otherwise, if the player has less points than I plus 17, then the player lost and we subtract. And this should be a plus equals, and this is a minus equals. And if it's exactly the same, then we have a tie, which is a push, so we don't need to do anything. And finally, let's return our expected value of standing. So next, let's actually call the function that calculates the expected value of standing. So at this point, let's give the user a menu of options to choose from with this program. Let's let choice number 1 be going through the dealer probabilities we just did. And let's let option 2 being exploring a player hand. So if the user enters a 1 from the menu, we'll run through all that code we did for the dealer. Otherwise, if he enters a 2, then let's prompt the player for what player hand he wants to analyze. And we'll call that PC1. And we'll also have him prompt the user for a second player card and the dealer up card. So let's also declare PC1 and PC2 for the player's initial 2 cards. And now let's call that player function. So but before we do that, let's also declare a variable for the expected value of standing. And in fact, while we're at it, let's do the same thing for hitting, doubling, and splitting too, because we will eventually get to those. So the expected value of standing is whatever comes back from the player stand function, and we send over the player total, which is player card 1 plus player card 2 at this point, then the number of aces, so we're going to send it 1 if player card 1 is a 1, otherwise a 0, plus a 1 if the second card is an ace. Then we send over a 2 for 2 cards and the array deck. And before I forget, let's take out from the array 1 for whatever the first player card is, the second card, and the up card. And from the total number of cards, we subtract 3. So let's tell the user the expected value of standing is whatever our function says it is. And I just realized that I forgot to declare the player stand function. I realize I made a mistake here. Where I'm testing for a dealer blackjack, I should have checked for a player total of 11, not 1. So this looks good, so let's compile it. And it compiled, and now let's run it. So let's enter anything. How about, always a difficult case in blackjack, is 2 player aces against a dealer ace. And that's telling me that if I were to foolishly stand on 2 aces against an ace, I would expect to lose about 77% of my bet, which looks right to me. Let's test another one. How about this one? Common situation. Player has a blackjack and the dealer has an ace up. The player gets offered even money. Should he take it? The answer is no, because you can see the player can expect to win 1.03883 times his bet if he declines the insurance. So 1.04 is more than 1, therefore the player should just say no. And I assure you I tested some other values and they all looked good. So I think we're ready to move on to calculating the expected value if the player hits. Next, let's write a function to calculate the player's expected value if he hits. So this program is going to need to know the player total points before he hits, the number of aces, the number of cards, and the deck composition. And again, the number of cards is only pertinent to determine if the player has a blackjack or not. I could probably do this without that, but I would have to use other tricks, so I may as well just count the number of cards. And let's call whatever the player's next card is, next card. So let's cycle that from 1 to 10. So first let's calculate, let's create a variable called prob to be the probability of getting any given rank, and that's going to be the number of cards left in the shoe of that rank divided by the total number in the deck. Then let's subtract the count of that rank by 1, whoops, as well as the total number of cards. So once the player hits and gets whatever the next card is, he is going to be put to a stand or hit decision. So we're going to need to know the expected value of both. So for the expected value of standing, we already wrote a function to calculate that. That's player stand, and to that we pass to it the player total plus whatever that next card is, the number of aces, which was the previous number of aces, plus if next card is equal to 1, let's pass it one more ace, and the number of cards, which is going to be our old number of cards plus 1, and then the deck composition. And how about the player has another option? He could hit again. So let's call that the expected value of hitting again. So let's declare that. So we're going to call the player hit function recursively to calculate that. And we pass to that all the same things we pass to the player stand function. Now, I happen to know that this program is going to take a long time to run if we calculate the expected value of hitting big totals. So to speed things up, I'm going to say that if the player total plus the next card is less than 17, then we go ahead and see what happens if we hit again. Otherwise, we're not. And we're going to just say the expected value of hitting again is -1, so that the program will make the player stand with that 17 or more. So our expected value of hitting, let's initialize that to 0.0. So we're going to add to our expected value of hitting the probability, which we already defined, times the greater of the expected value of standing and the expected value of hitting again. And I need to create a function to return the greater of these two values. Simple enough. So after we've done that, we can put back that card back in the shoe. And let's return the value of the expected value of hitting. And let's declare these new functions at the beginning of the program. Don't forget the semicolons. And down here, let's show the user what happens if the player hits. Okay, now let's compile this, and it compiled, and let's run it. So let's put through a couple of frequently misplayed hands. One of them is a player 12 against a 3. This is a hand where most players stand. But here we can see that if the player stands, he can expect to lose about 25.5% of his bet, as compared to hitting, where he loses only 23.1%. Therefore, the player should hit a 12 against a 3. Let's try another one. How about a soft 18 against a 10? Now let's make it against a 9. So an ace and a 7 against a 9. So this is showing us that the player can expect to lose 18.3% of his bet if he stands, and only 9.8% if he hits. You see almost every player misplay this at the table, probably thinking an 18 is good enough for me. But against a 9, an 18 is not so strong, and you get 2 chances to improve the hand by hitting. So these numbers look correct to me. So next, let's move on to doubling. Next in this video, let's see what happens if the player double downs. And this is going to work a fair bit like the hitting function. We need to pass to it the player points before he doubles, whether or not he has an ace, and the deck composition. And as before, we're going to, in fact, let's copy and paste this code up here. We're going to cycle through the 10 possible cards the player might get after doubling. So let's declare next card and the probability of getting any given card, and a new variable called EV double for the expected value of doubling. And let's initialize that to 0. And to save some time, it's pretty obvious the player should never double with 12 or more. So if the player total is greater than 11, we're going to say that the expected value of doubling is equal to -1, because there's always going to be a better option. Otherwise, we will loop through whatever the next card is. So we can get rid of this code about hitting. So as you know, when the player doubles, he gets one more card and that's it. He can't take any more even if he wants to. So the expected value of doubling is going to be the probability of getting any given card times the expected value of standing with that 3-card total, times 2, because the player is betting twice as much. So we're going to give the player another card. We're going to send over to the player stand function his old total plus the next card, the number of aces, and we know the number of cards is going to be 3, and the deck composition. And we're going to return from this function the expected value of doubling, which we just calculated, times 2, again because the player is betting twice as much. So let's declare this function at the beginning. And then call it. So in this case, we do not need to pass to the double function the number of cards. And let's show the user what we get for the expected value when we double. So next, let's compile it. And it compiled, and let's run it. So let's put through it another frequently misplayed hand, being a soft 18 against a dealer 6. Again, this is one of those situations I think most players think an 18 is good enough for me, I'm going to leave it alone. But let's see what happens. So this is telling us if the player stands he can expect to win about 28% of his bet. If he hits, 19%, and if he doubles, 38%. So doubling is by far the best play in that situation. So these numbers look right to me, and I think we're ready to move on to splitting. Next in our video, let's write some code to see what happens if the player splits. And logically speaking, it's going to be a lot like the player doubling. So I just copied and pasted that code. And let's change the name of it to player split. And let's change the name of EV double to EV split. And okay, so much like with the doubling function, we're going to cycle through whatever is the next card the player will get on top of the card that he split. So first, as before, we're going to find out the probability of getting that card, remove it from the deck, and then after the player gets that next card, he has the choice. He can either stand or he can hit. So let's calculate the expected value both ways and take the greater of the two. So here we're saying the expected value of standing is whatever we get from the player stand function by passing to it the player total plus the next card, and then adjusting for the number of aces, and we're going to send to it 3 for the number of cards. Even though there are only 2, we're going to send it 3 because let's say that the player splits aces and gets a 10. That's only going to count as 21 points, and if I were to send an ace and a 10 with 2 cards to the player stand function, it would return 1.5 for getting a blackjack, assuming the dealer didn't have a possible blackjack. And we don't want to do that. So I'm going to trick that player stand function by sending it 3 cards. So it will treat an ace and a 10, for example, as just 21 points. And we also are going to call the hit function. And we are going to send that the same information, except with the hit function we can be honest and send it just 2 cards. And our expected value of splitting, is going to be the dot product of the probability of getting any given card times the maximum of the expected value of standing and the expected value of hitting. And after we have run through all 10 possible cards the player could get, we're going to multiply everything by 2 because the player is doubling his bet. However, we need to make an adjustment in the case of splitting aces. If the player splits aces, he gets 1 card only, that's it. He cannot split again. And he cannot take more than 1 card. So I'm going to say that if the player total is equal to 1, meaning the player split aces, then the expected value of hitting is equal to -1 to force the program to accept the standing value. And if it's not a 1, then we call the player hit function as I just explained before. Next, let's declare the player split function. And let's go down here for our code that tests out any given hand. So as you know, the player must have a pair to split. So I'm going to say if player card 1 equals player card 2, then EV split is equal to player split, and I'm going to send to it just one of the cards. And I'm going to send to it a 1 if that card is an ace, and a 0 otherwise, and the deck composition. And I do not need to send to it the number of cards. And if the two ranks are different, PC1 and PC2, then I'm going to say the expected value of splitting is -1 because the player is just not allowed to do it. And let's tell the player what that expected value of splitting is. And here, this should be a PC1 or a PC2, not just PC, because there is no variable that's just PC. So let's compile this, and it compiled, and now let's run it. So let's try 2 8s against the dealer 5. So you can see here that splitting 8s against a 5 is by far the best play, with an expected value of about 15.0%. And that looks right to me. Let's try another one. How about splitting aces against another 5? And the program is telling us that, again, that's by far the best play is to split aces against a 5 with an expected value of about 63.4%. And these numbers look right to me. So at this next point in the video, we are ready to consider analyzing the whole game, not just one hand at a time. And finally in our video, let's analyze the whole game, every single possible starting situation, as opposed to testing out one at a time as we have been doing. So if the user enters a choice 3, then we will analyze the whole game. So let's start by cycling through the first player card from 1 to 10. And then for the second player card, we can start from the first player card and go up to 10 to avoid analyzing the same situation twice. And now let's analyze the all up cards from 1 to 10. And we're going to keep a running calculation of the probability of any given hand as we go. Let's start that out at 1.0. So we're going to multiply that probability of 1 by the probability of any given player card 1. And then let's take that card out of the shoe. And now let's multiply that probability by the probability of the player's second card. And let's multiply that by 2 if the two cards are different, because it's two different situations. For example, a player 5 and a 6 is the same thing as a player 6 and a 5. So if the player card 1 equals player card 2, then we're just going to multiply by 1 because we only need to run through it once, and 2 if they're different. now we come to the up card. So we're going to do the same thing. Multiply the probability by the probability of that up card. And then take it out of the deck. And then, as we come out of this loop, we're going to do the opposite. We're going to add that card back in. As well as dividing the probability by the probability of that card. Basically just doing the opposite. And so here's where we come out of the loop that is cycling through player card 2. And let's not forget our term to multiply by 2 if the cards are different. And finally, the same thing for player card 1. So in the middle of all this, let's actually do something. And for that, we can grab our code up here to call these functions to get the various expected values. And once we have all these expected values, let's write them out. So when I'm writing out a lot of statistics, I like to use printf because I found that cout and carr tend to have a limited size buffer and things don't come out in the right order, but printf is much more dependable. So first I'm going to print out 3 integers for player card 1, player card 2, player card 3, and then 4 floating point variables. 1, 2, 3, 4. And I'm going to send to that printf function player card 1, player card 2, the up card, I'll start with the expected value of standing, and the expected value of hitting, then the expected value of doubling, and then the expected value of splitting. And let me fix this typo here. Should be up card. And up here at the beginning, let me create a couple more floating point variables. Let's create one called one for the total probability, and let's initialize that to 0.0, and another one for the expected value. And again, initialize that to 0.0. And just to make sure that we're doing our math correctly, when we get here to inside the up card loop, let's increment the total probability by the probability, and let's calculate the maximum expected value. We'll call that max EV. So max EV is going to be equal to, we can say it's going to be the maximum of the two, between the expected value of hitting and the expected value of standing, and the expected value of doubling and the expected value of splitting. So that should give us the highest expected value of 4 different inputs. So let's add to our maximum, our total expected value by the probability times the maximum expected value. And at the very end, let's tell the user what that is. And let's also export the total probability. And I'm sorry, this should be the total expected value. Finally, if we ran this program right now, it would show you what the player's expected value is, but this was a lot of work for just one number. So let's also show you the basic strategy. So I'm going to be putting that in the form of an 11 by 11 by 11 matrix according to the player's 2 up cards and the dealer's up card. So down here is the point where we have the maximum expected value. So let's say if the maximum expected value is equal to the expected value of standing, then let's say that that basic strategy for that hand, PC1, PC2, and up card, is equal to, let's call it a 1 for standing. And if the maximum expected value is that of hitting, let's send to our basic strategy a 2. And if doubling is the right play, then let's send it a 3. And otherwise, let's send it a 4. And let's put in another else here. So that should populate our basic strategy properly. And now let's go down here and print it out. Well, first, let's do it by category. So first, let's do the hard totals. So let's go from PC1 is equal to 2, and we're starting with 2 because we're only looking at the hard totals. And let's go up to a 10. Now let's only go up to a 9. And for the second player card, let's start with PC1 plus 1, and let's have PC2 go up to a 10. And let's cycle through the up card from, now let's start with 2 and go up to 10. And we're going from 2 to 10 because we're going to put the ace column at the end. So you'll notice that I used a %C here for a character. So let's print out the letters instead of numbers for the basic strategy table. So let's create a string called codes. And for a 0, which it should never be, we'll do an X. Then we have stand, hit, double, and for a P, and we'll do a P for splitting, per a convention that I think Lawrence Revere started. And then finally, let's do an ace. And I forgot to put quotation marks here, so let's do a character and then a comma. And I forgot a semicolon here. And here let's do our character and then a carriage return. And now let's do the soft totals. So for the soft totals, PC1 is always going to be a 1. So let's range the second player card from a 2 to a 10. And for PC1, we're just always going to use a 1 for an ace because it's a soft total. And finally, let's do the pairs. And for that, let's range PC1 from 1 to 10. And we're going to send PC2 as the value for both player cards. And I forgot to send over the basic strategy in the form of a character by putting it in the codes array. So let's fix that. And let's also show the user the 2 player cards. And in the case of and this should say soft totals here. And for the soft totals, the first card is always going to be a 1. And for the pairs, we're going to repeat PC2 twice. And let me correct another mistake. Here where I'm printing out the column for the aces, I should use just a 1 for the up card. And let's compile this. And it compiled, and now let's run it. And I'm going to save the output to a file here. And I will call it out3. And let's wait. Now let's take a look at the output of the program. So here is the output from our program. First, it shows the expected value for all combinations of the player's first 2 cards and the dealer's up card for both standing, hitting, doubling, and splitting, except where you're not allowed to do 1 or it's completely unreasonable, like doubling on a 19, for example. And after all that, it's showing the total probability is 1, which is what we expected, and the house advantage is about 0.69%. In other words, the player can expect to lose about 0.69% of all initial bets. And here is our basic strategy. And feel free to pause this at any time, and you will see that it agrees with the published sources. And again, remember that this is based on the European rules where the player loses everything if he doubles or splits against the dealer blackjack. Therefore, you're not going to be seeing things like splitting 8s against a 10, because it's more dangerous if the player loses 2 units when the dealer gets a blackjack. Another interesting thing is, notice here, if the player has a 2 and a 10 and the dealer has a 4, this says the player should hit. This is a composition dependent exception. I really want to emphasize that this whole program made a perfect combinatorial decision every single time. And sometimes that was a little bit different than basic strategy. However, if we look at, say, a 3 and a 9 against a 4, it says stand. A 4 and an 8 against a 4, it says stand. And a 5 and a 7. And if we took a weighted average of all those ways to make a player 12, the balanced decision would favor standing. And here's our soft totals, and here are our pairs. Before I get into my final words, let me check that house advantage against that on my site. So let's put in the right rules. 6 decks, dealer stands on a 17, no double after a split, split to 2 hands only, and player loses everything against the dealer blackjack. And here we can see that the house advantage under those rules is 0.68647%, which rounds to 0.685%, the same house advantage that we just got from my game. But I phrased it as the player's expected value, therefore it's negative. Now, if you're not impressed that I'm comparing my own number to my own number, feel free to look this up in any respectable blackjack book or source, and you will see that we probably agree within 0.03%. Why is there a little wiggle room? It's because some sources use a random simulation, some assume a cut card, some, in fact, most of them assume total dependent strategy as opposed, a total dependent strategy as opposed to a composition dependent strategy as I just did. So with that, let me wrap up this video. Well, thank you for making it to the end of this video. This is by far the longest video I've ever made, and I appreciate you watching the whole thing. I hope that at least a few people do. So why did I make this whole video? I did it partially out of just my love of math and computer science and hope that it inspires some beginners in computer science to take it further, to see what it can do. And also I want to address this myth that the basic strategy is wrong. And the way it usually goes is that Ed Thorpe, back in the 50s or 60s, programmed blackjack on a UNIVAC mainframe and made a bug somewhere, and for 60 years every other blackjack expert like me has just been mimicking his error like lemmings. No, blackjack has been analyzed over and over and over, probably by hundreds of people, probably mainly just blackjack hobbyists that could code. And I hope that one thing that I convey from this program is blackjack is not that complicated. My program was just brute force looping. Everything that I did in this program you can learn in an introductory computer programming class. It's basically just basic arithmetic, for loops, and if statements. That's it. It's just simple logic and brute force looping. So anyway, I hope you enjoyed the video and learned something from it. Please leave your comments below, and I look forward to seeing you in another video. And I already have some where I analyze other casino games, and I plan to make more. So again, thank you for watching YouTube, and I'll see you later. Bye.